Hello, how are you all doing today? I'm Bernie Thompson, President of Automotive Test Solutions. Today we have a 2003 Chevy Silverado with a 5.3. This vehicle has low power. We need to diagnose this car by the time we get around the block. Hop in and let's go for a ride. Let's take a look at the EScan by ATS. We're going to open up the software. The EScan is a PC-based scan tool that has a VCI that connects to the bus on the vehicle. That gives me communications and we pull data from the modules. However, with this data we do very unique testing that no other scan tool in the world does. So one of the things that we're going to do is immediately I can see that bank 1 and bank 2 are good. We have good control. We're switching rich to lean, and we have a centered lamp on. The centered lamp indicates we have good control. But we got to look at this. Bank 1 has a heavy fuel trim and bank 2 doesn't. So we have a difference between our trims. Now, bank-to-bank fuel trim is 17%. Now, 17% is a large amount of trim to have a problem between bank-to-bank. This is indicative of a single bank problem. So this isn't something that's universal to the engine. This is something on one side compared to another. We also have low vacuum, and we have several DTCs set. Let's look at our DTCs. So our DTCs are the mass airflow has a range or performance problem. We have also multiple misfires on the engine. The catalyst efficiency on bank 2 has a problem, and we're lean on bank 1. Now that doesn't tell me what I really want to know. I want to know how to fix the car before I get off my drive around the block. We're going to run a test which is fuel trim. Now this is total trim, long-term plus short-term. We're going to start the test, and once you start the test, you're going to drive this car just normally. And what we're going to do is we're going to fill in these cells dynamically. So these cells are just going to start to fill in, and they're going to fill in as we're driving the car. Whenever you're looking at any type of a fuel system problem, you always want to do these type of tests dynamically. We really want to see what these cars do over the range that they're in. Now that we've loaded this table, we want to go ahead and we want to look at the data to see what we've got here, okay? So what we have is we have a heavy add on bank 1 and a heavy subtraction on bank 2. So bank 1 is adding a lot of fuel and bank 2 is taking away a lot of fuel. Now this problem would indicate something. If I had overhead cams, one of the cams could be out of time on one head, but on this 5.3, our cam is in the block, so that's not going to be our problem. This is going to be something more related to the airflow, such as a restricted exhaust. So in order to check that, what we want to do is we want to go to the volumetric efficiency. We're going to start the VE test. What a volumetric efficiency test does is it rates how much air is entering the engine. We want to set up the temperature for the day, and our day is 50 degrees at our test site right now. So we're going to start the test, and what we do with this test is we start to roll, and then we floor the car wide open. Now I want you to notice the yellow trace is moving up and down. That's the airflow going into the motor being read directly from the mass airflow sensor. Now the sensor is reading up and down because it has heavy turbulence. So the turbulence are created by possibly a restricted exhaust on one side. So if the air can't get out one side and it can free flow on the other, I have heavy turbulence. I also want to note that basically I'm only flowing about 70 grams of air, but the model, which is a theoretical model that only the EScan has, this is how much air this engine should flow. Well, I should be at 130 grams of air, but I'm not. I'm way down at 80 grams of air. So with less air, that's less fuel, and this creates a power problem. Let's look at the power. The horsepower should be making somewhere about 160 on this engine, but we're only producing maybe 110. This is also proving that we do have a lack of power on this car. We can feel it when we drive it, and that was what it came in for the complaint. We want to run a cat efficiency test. Now the cat efficiency test is going to be conducted with the post and pre-oxygen sensors. We're going to watch the front oxygen sensor and the rear oxygen sensor of the cat. What we're looking for is one of these cats to be partially plugged. That means that the efficiency is going to drop off. You want to get the car going about 30 miles an hour at a steady state, and we want to just keep it at a steady state throttle. And as we keep this steady state throttle, what we're interested in is we're interested to see what the two cats are going to do. I can see that bank 1 is in the 80s and bank 2 is in the 30s. Now this is a problem. This shows you that bank 2 has a restriction. In other words, to have catalyst efficiency, I have large surface areas needed. If I cinder, burn, or carbon plug a cat, we'll lose some of those sites, and those sites will drop our efficiency. I want to run one more test, which is a fuel efficiency test. Fuel efficiency is how well the fuel is being used, or the thermal energy of the fuel is being used to move the vehicle weight. So we want to go ahead and start this test, and what we're going to do when we start this test is we go to 40% throttle opening, and we want to hold it very steady, about 40%. This car should be somewhere in the 20% range for our efficiency. We can see that we're at the 11% range, which shows that the fuel is not being efficiently used to move the vehicle's weight. The engine is impaired in the power, which means the fuel is just being wasted. So let's pull over and take a look at our data sets that we have. So we want to review our data sets right now, right? Okay, we got fuel trim, we have heavy adds on bank 1 and heavy takeaways on bank 2. Volumetric efficiency has heavy turbulence, is only flowing half of the air that this engine should under load. That's a problem. The power is also impaired, so our horsepower is only half of what we should be making. The fuel efficiency is only 11%. It's half the efficiency that the engine should be operating with. The catalyst efficiency chart clearly shows us that we have a problem with the efficiency on bank 2. Now we know, before we're off of our test drive around the block, that cat 2 is plugged. Now that we've replaced this plugged cat on this 2003 Chevy Silverado, and the cat is plugged, let's take a look. Let's go ahead and hop in and go for a ride to test the data sets. Now that we have this vehicle fixed, we've put the catalyst on bank 2. Let's take a look at our data sets. First off, I want to note that bank 1 and bank 2 show that I'm going rich and lean. The biggest thing I want to notice is the center lamp is on. Now, just because I'm switching rich and lean doesn't mean I have good fuel control. The center lamp is indicative that I have very good control on both banks. The next thing I want to notice is bank 1 fuel trim lamp is green and bank 2 fuel trim lamp is green. These being green shows me that the fuel control is good now. It's less than 10% long term. So remember, before we had a huge variant here, and that was displayed on bank-to-bank fuel trim. I now have less than 1% difference. Now anything more than 5, you have a problem, but 1 to 2% is more normal, and that shows that I have good control at idle. I also have good vacuum now, and I still have codes set, but they've matured to pending codes due to driving the vehicle after we've had this repaired. We're going to go to the sharpshooter. We're going to do long-term plus short-term, which is total trim. It's a unique test just to the EScan. In order to do this, we're going to just start to drive the car, and we're going to drive it normally. We want to pull over and we want to look at our data set now. Now the data sets are going to show us that we have a difference that's occurred now. So when we look at this, we can see that our fuel trim down in the idle position is okay, but as we accelerate, the fuel trim is off basically 15, 16%, 17%. But the difference between bank 1 and bank 2 is apparent. Bank 1 was adding in the high 30s, and bank 2 was taking away in the high 30s. Now we can see that both banks are adding about 15, 16, 17%, but it's universal. So this problem is more universal to the car. So what we want to do now is we want to run a volumetric efficiency test. So we want to go in and we're going to go ahead and run this. We want to put our temperature and set it for the day, and that's going to be about 41 degrees. So this is going to give us our overall how much air the engine can pump. What we want to do is we want to start to accelerate and then open the throttle wide open and let the car rev. And then what we want to do is take a look at that data set and see what we've got here. So basically we're going to stop, and the first thing that we want to note is that the yellow trace, which is being reported directly from the mass air sensor, is very smooth. I don't have all the turbulence, and I'm not reading way away from my model. My model is in red and my mass air is in yellow. Now you can see that they're very close. The difference between these two is given over here. Do you see how we're at 14–15%? So the air is misreading, and that is equivalent to what the fuel trim is doing. So these two show that I'm not quite reading my air correctly and I'm having to trim for it. So the mass air has a calibration issue. We want to look at the power though. We can see now that we're making almost 230–240 horsepower. Now before we weren't even close to this, and note how smooth our horsepower is being made, and it feels like we're running good. So we fixed the original problem, which was the horsepower or a power problem. We now want to run a catalyst test, and when you run the catalyst test, we're going to take the front and rear O2 sensors and we're going to compare them to each other. Now the one thing that we want is we want the front O2 having rich lean cycles, but we want the rear O2 very steady. So what we want is the rear O2. We really don't care if the rear O2 is high or low. What we're really worried about with the rear is that it's not moving with the front O2. We can see now that it's not running with the front O2, and we're in the high 90s on our percentages. We're doing a steady state cruise at about 35 miles an hour. So that would show us that the cat is now taken care of. Now, one thing to remember with the cats, in order to have efficiency, you have to have a large amount of surface area exposed, so as the hydrocarbons and the CO are going out, we can convert them on the sites that are present, the precious metals that are in that cat. Now what we want to do is we want to go ahead and we want to run the fuel efficiency test. Now the fuel efficiency test is going to rate how we're using the fuel's thermal energy to move the weight of the car. We're going to go ahead and we're going to accelerate to 40% throttle. We want to hold that very steady. We can see that we have 20% efficiency, which is way better than the 11% that we had previously. So now we're actually using the thermal energy from the fuel quite efficiently, and that's what we would expect from an engine. We want it to run good. Now anything that would load this car down or have rolling resistance would also decrease this. So if I had a few tires that were low, or we have bearings dragging, or we have brakes dragging, that would reduce this as well. So let's go ahead and go over our data sets again. The fuel trim is good at idle, and as we load the car, we start to get into the 14s, 15s, 17s. And if we look at our volumetric efficiency, we also see that the air is under reading, and we're also at the 14, 15, 17 range. If I go to the power though, we're at quite good horsepower at 230–240 horsepower, which is indicative that we have fixed the problem and we don't have the turbulent activity that we had earlier. The fuel efficiency is at the 20% mark, and the catalyst efficiency is in the 90% range. That would show you what the problem was prior to us fixing it and what problems we might still have. In order to see these type of problems, your shop is going to need an EScan, because there's no other scan tool on earth that runs these tests for you this easily.